Welcome back to Cloud 42, I'm James. Today we're continuing work on the 2x72 belt grinder. If you didn't see part 1, there will be a link to the playlist down below, and you might want to begin at the beginning. There were a number of comments on the last video asking where to get the plans for the grinder if you want to build your own. The files are available through my Patreon page. There is a link in the video description down below where you can sign up to become a patron and help support the channel. And if you do that, you can download files for this and all of my other projects. The file bundle for the grinder project contains everything you need to order the laser cut parts from Send Cut Send if you want to, who by the way are sponsoring this build, or you can use the DXF files to cut the parts out yourself with a plasma cutter or a water jet or whatever you have access to. The second most popular, or maybe the first most popular question on the last video in the comments was, what does it cost? What's the total BOM cost for the grinder? And that's a difficult question to answer. I can tell you that the way I built it with the powder coating and with a high-end dust-sealed VFD came in a little under $2,000. But if you want to build it differently, the price could be quite a bit lower. If you want to use an Asian import VFD, that'll knock $300 or $400 off of that price. If you want to forgo the powder coating and spray paint it yourself, it could go down even more. If you wanted to order a couple of sets of parts for you and a friend, price goes down some more. And you could get it down to the $1,300 range. Or if you want to cut the parts out yourself, it could be even cheaper than that. So the price really depends on how you want to build it. In the last video, we got the frame assembled, and this time we're going to work on the tension arm and the belt tracking mechanism. So let's get started. The arm pivots on a couple of oilite flanged bushings, and those bushings are held in a couple of aluminum rings that are screwed to the sides of the arm. I was originally going to weld some tube to the steel of the arm, but when I decided to go with the powder coating, that really meant the welding was out and I needed to use screws. Thought about 3D printing the parts. I even had some prototypes, but ultimately decided I needed to make them out of aluminum. So I grabbed a slug of aluminum out of my scrap bin, and we'll start here by just facing off one end and then turning it down to the right diameter. I'll start by just taking a light cut across this to clean it up. Then I will take a measurement of that and enter that diameter into my DRO. And then from here, we can just work with the numbers on the DRO. You can see here that I'm getting long, stringy chips that want to wrap around the workpiece. This is super common with aluminum. The solution turns out to be to just take a deeper cut on each pass and a faster feed. So you're taking a wider cut per revolution, and you can see that results in thicker, heavier chips that break more easily. As I get down close to the dimension, I'm going to take a finer cut so we get a good surface finish, and as you can see, I'm back to the stringy chips because of the finer cut, and those chips themselves are kind of scraping up the surface and messing with my surface finish, but it's nothing that a little Scotch-Brite can't take care of. Note that I'm reaching under with the Scotch-Brite so that if it hooks or something, I don't end up jamming a finger. Now that we've got that to diameter and got a reasonable surface finish for the outside, I'll go ahead and just punch a hole through it. This hole needs to be just over 625 thou. The bushings go into a 5/8 hole. They're actually slightly oversized and need a little bit of compression. So if we get the hole slightly over 5/8, we should be in business. I'm just starting here with a 1/2 inch drill because it's the biggest one that will fit in my tailstock drill chuck. And then we'll come back with a boring bar. Just checking here to make sure we can reach to the depth that I need, and we'll come back and start with a light pass to establish our dimension. We'll just make a pass through here. And that's cutting nice and smooth. The drill ended up being pretty centered, so this is a nice even cut, but you never really know on the first pass. We'll take that all the way to depth, pull it out, and then get a measurement. I'll use a 3-point internal mic here just because I have them, but you know, there's lots of ways you could measure this. You could measure it with pins. You could do it with the inside jaws on a caliper, but since we are trying to fit a bushing, that may not be quite accurate enough. I've got a dimension now. I'll enter that into the DRO. And from here on out, as long as the final cut we take is about the same depth as the initial cut we took, so that the tool pressure and the spring back of the tool are similar, we should be able to just follow the dimension on the DRO. And so we'll get down here, take one final fine cut, and measure to see where we are. And that's just over 625. That's exactly where we want to be. Break the edge on the outside, and I'll raise the tool above center line so I can get a chamfer on the inside without fouling on the bottom of the tool. And then we can part it off. I'm using a carbide parting tool here, but I have honed the edge with a diamond lapse, so it's razor sharp, and that makes it cut really well in aluminum, even though the geometry stock isn't optimal in aluminum and certainly not optimal for a small lathe. High-speed steel with a good keen edge often works better in this situation, but this is what I had. The key here is just to make sure that we keep lubricant down in the cut so that the aluminum doesn't ball up and gall up and jam in the cut, snap off the tool. Then we get close, you can kind of hear it, and we'll just catch the part with the back end of the brush. Got two of these to make, so I'll go ahead and face off the end, break the edges again, and part off the second piece. Now I am parting these off a little bit long, so we will need to come back and face the other side. I have an aluminum spider here in the 3-jaw chuck, and that serves as a spacer to hold the part parallel to the chuck out near the ends of the jaws, so I have access. This also provides a depth stop, so I can make a facing pass, I can take the part out, measure it, put it back in, make another pass, and I can bring it to exactly the final dimension. Final thickness of this part should be 438 thou, and it looks like we are pretty close. We're plenty close for a belt grinder tracking arm pivot. These will work. This is my mini pallet, and you can see that I already have a deep scar in it, so you don't have to feel bad when I drill into it. I consider this a sacrificial fixture, and it's served me pretty well over the years. I've got a couple of small strap clamps here that I made after Tom Lipton's design, and as with Tom's design, I'm using 1032 screws to hold everything down. And this should be plenty for this operation. To find the center of this, I'm going to start with a 1/2-inch pin, again because a 1/2 inch is the largest pin that will fit in this chuck, and I'll just use this to kind of roughly find the center, and then I will bring in the dial test indicator to fine tune the position. And you can see I didn't get very close with the pin, so had a little bit of work to do here, and let me tell you, the process of dialing in and finding center with a dial test indicator like this goes much, much quicker if you turn the mill handles in the correct direction. Keep going the wrong way, it takes a lot longer. I've got this within a few tenths, so that will be fine. Honestly, within a thou or two would have been plenty for this. I'm using the bolt hole pattern feature of my DRO, and I have it set up for a 6-hole pattern. Even though there are only 3 holes in each one of these rings, there will be 6 in the arm. I just went ahead and set it up for 6, and I'll just advance it 2 holes at a time. I'm starting here with a 120-degree spotting drill and just making some spots for the screw holes to make sure that I get good, accurate locations. And if you listen, you can hear that the DRO is just incessantly beeping. And what it's doing is when you get close to the position of the next hole, it starts beeping until you get exactly there. You get even a 10,000th of an inch off, and it beeps. And, you know, even just turning on the mill is going to move it a 10,000th of an inch. So it just beeped the whole time. There's got to be a way to change that. I haven't figured it out yet. Haven't really looked. Eventually, it'll bug me enough if I use this feature, and I will fix it. Follow up the spot with a clearance hole, and this is a pretty close fit clearance hole for the number 8 screws I'm going to put in here. And with all 3 of those holes through, I'll bring in the countersink. This is an 82-degree countersink because these are imperial screws with an 82-degree cone angle. And there's the beeping again. That's beeping for X and Y. It beeps twice as fast if you're off by a 10,000th of an inch in both axes. Just figured out how deep that needs to go, and I have set a stop on my quill. And I'll just go around and do the other 2 holes. That's one part complete. We'll just take it out of the clamps and repeat the same process for the other one. Looks good. I can't complain. I mean, I could, but I won't. To put the threaded holes in the arm, I'll use the same mini pallet setup with the same clamps, but I will put some pieces of paper underneath the strap clamps just because I don't want to mess up the powder coat. It's too pretty. I don't want to do that. Normally you do all the machining before you powder coat, but when you order the parts laser cut with the powder coat on them, you don't really get that choice. A little bit of paper should protect this. The surface of the mini pallet itself is smooth and flat. I stoned it just to be sure. And so there's nothing sticking up that should mess up the powder coat on the bottom. Get this snug down. Since we're really only drilling and tapping holes, there isn't going to be a lot of sideways force on this, so this should be plenty. Didn't want to get the pin back out, so I'll just use my countersink tool here to center up and then grab the dial test indicator. Now this is a laser cut hole, so it is not going to be perfectly round and smooth. It does have the powder coating on it, which helps some, but there is going to be a little spot where the laser started and stopped. I actually got a comment on my last video complaining that I wasn't being fair to my sponsor, Send Cut Send, because I said that the parts weren't perfect. Like maybe they thought I should have been shilling harder or something. It was odd. That's just the reality of this. It's a laser cut part. That is a limitation of the process. And you need to understand that if you're going to order parts and use them using that process, regardless of who makes them. So I've got my 6-hole bolt pattern set up again, and we'll just go around and do exactly the same as before and spot all 6 holes. And of course, just as before, the DRO is continuing to beep because I'm a 10,000th of an inch away from the ideal position. Just ignore that as usual. And let's switch over to the tapping drill and drill these out for tapping. I will brush some lubricant on here, and it looks like I actually grabbed the wrong bottle, and what I'm actually brushing on here is A9, which is the lubricant that I normally use for aluminum, instead of a standard cutting oil or a thread cutting oil that I would use in steel. Oh, and by the way, use just the tip of the brush. You could see there I kind of caught the side of the brush, wrapped some bristles around the drill and ripped them out. But if you just brush lightly with the tips of the bristles, it puts some oil on the drill and it knocks the chips out of the flutes. That's all 6 holes there. Blow off the chips just so you can see what's going on. It's not really necessary. And we'll put in the tap. Now this is not a spiral flute tap. It's not a spiral point tap. This is a form tap. A form tap doesn't actually have cutting edges, so it doesn't actually cut away material. It forces the material into the shape of the threads. Has 2 or 3 lobes on it that reach out to the full thread diameter with some gaps in between for lubrication to get in. And it actually just squeezes the material into shape and causes it to flow in between the threads of the tap. This has a number of advantages. In materials that work harden like stainless, the threads can end up being quite a bit stronger, and even in materials like mild steel and aluminum, the threads can end up stronger and smoother because you are actually forming the metal and changing the grain structure in the tap area. The taps also tend to last longer because they don't have sharp edges that get dull, and they're a lot stronger because they don't have flutes cut into them for chip clearance. Those are the 6 holes. I'll make sure there aren't any chips in them and we'll give them a try. And these feel really nice and smooth. Those will work. Down at the other end, we have 1 hole that needs to be tapped 3/8/16 for the tracking adjustment knob. And I'll just use a pin in the drill chuck to locate this. The hole that was cut with the laser should already be the correct tapping size for this tap, and it's a big enough, coarse enough tap. I didn't even measure it. I'm sure it's fine. Just lube it up really well and run it through the hole. Now the powder coat does actually make the actual hole in the part smaller than what was cut with the laser, but it's soft material and the tap just wipes it out, so this isn't an issue at all. Holes on the front side look nice and clean, but on the back side, we definitely have some burrs to take care of. Started out with a Noga rotary countersink and then realized I have power tools. I might as well use them. So I just put the chamfering bit back in and floated this around and trimmed up all the holes. Those look nice and clean. This part should be ready to go. The last two parts we need to machine are for the tracking assembly. There's a yoke that screws onto the tension arm and a plate that pivots in that yoke and holds the axle for the tracking wheel. These parts need to be machined from several sides, so it didn't really make sense to have them laser cut. It's much cheaper to just machine them from some pieces of mild steel bar. These are 1 inch wide by 1/2 inch thick, and this is designed to just use those dimensions. So we don't need to machine all of the surfaces. We just need to machine the ends that were saw cut. I have these cut roughly to length, but we'll come in with a 1/2 inch end mill and clean up one end of each. We don't really care about the length at this point. We're just trying to get a clean, flat, perpendicular surface. Because I have a spring holding the parallels in place, it's safe to blow the chips out with compressed air. They won't go anywhere. And then I'll just switch the parts here and I will machine one end of the other. Tapping these down with a chunk of copper just to make sure that the parallels are tight. If they weren't down on the parallels, the ends might not be square. That's not super important here. I mostly just didn't want the parallels to vibrate out and run into the end mill. Now with one end of each part cleaned up, we can flip them around and mill them to length. We'll just take a pass on the end, get it cleaned up, measure the length of the part, and then come back and use the DRO to bring it to the desired dimension. And I always double check just to make sure we're really there before I break down the setup. Then we'll swap places and do the other one. First one's supposed to be 1.5 inches. The other one's supposed to be 1540, and it looks like we hit those pretty much right on. We'll start with the larger piece here. This needs to have a threaded hole to hold the tracking wheel. I'll just put it here in the vise and use the half function in the DRO to find the center and use the edge finder to find one end. And I'll go ahead and enter minus 0.1 inches because I know the tip of this is 0.2 inches in diameter. And I'll go ahead and dial into 0 and just make sure that I got that correct. And that looks pretty good. Now, it does matter which end of this is the top, so I will go ahead and mark the top with a Sharpie so I don't get confused. Put in the tap drill for 1/2-13, move down to the correct location, and go ahead and put in the tapped hole. You'll note that I'm not spotting this hole first, and that's for two reasons. One is this is a short, large diameter drill, so it's really rigid. It's not going to wander anyway, and also because the exact location of this hole isn't that critical. Just go ahead and lean on it and push the hole all the way through the part. You can see that the flutes on this drill are not cutting evenly. We're getting one nice chip and one kind of stringy chip. That is a factory grind, so apparently it wasn't great from the factory. I may touch it up at some point, but it is working. Come back with a countersink here and put a nice chamfer on the edge and then just push the 1/2-13 tap through. And you can see I did not get it tight enough in the chuck and it was slipping there, but about the time I stopped to do something about it, it made it the rest of the way through. So we got our hole tapped. Note to self, use the hook spanner to tighten the chuck when tapping 1/2-13 in steel. Now the oil has kind of messed up my marks, so I will recreate them just to make sure I continue to know which end is the top. And then we'll go ahead and mount it with the top sticking out of the end of the vise, of course using the other part as packing so that we can put in the pivot hole. This should be a 1/4 inch hole that is reamed for a nice close fit on a shoulder bolt. So we'll start by spotting this one, drilling through one imperial size under a 1/4 inch. And then we'll come back with a 1/4 inch reamer and push that through the hole in a single pass. Now the shoulder bolt is actually ground. It's specified to be between 2 and 4 thou. under a 1/4 inch. So if we ream this right on a 1/4 inch, it should be a good fit. And it is. That's exactly what I'm looking for. Deburr those holes, and this part is done. We need to put the same 1/4 inch reamed hole through the yoke, but since it's going the long direction through the part, and I would need to go all the way through, I don't really want to hang it off of the end of the vise because I would have very little to hang on to. So I'm going to set up a stop here and we'll just go ahead and drill from both sides. Spotted that. Now we're drilling one size under a 1/4 of an inch, and then I'll come back with the reamer. Now this hole is not going all the way through. It's going a little over halfway through. The center of this part's going to get removed, so if the holes don't meet exactly right in the center, it doesn't really matter that much. So with one side drilled, I'll just flip it over, making sure I keep it in the same direction so the holes will line up, and perform exactly the same operations and put a reamed hole in from the other side. These should intersect perfectly, but even if they don't, the shoulder screw is going to be 2 to 4 thou undersized, so it shouldn't be a problem. Now we'll flip this around and put the 2 tapped holes in it that are required to mount it to the arm. I already have the Y0, but because this part is a different length, I'll go ahead and reestablish my X0 using the half function in the DRO. And then we'll come back and push in 2 1/4 20 tapped holes. And these also don't go all the way through, because if they did, they would hit the parallel, and they don't need to be because we're going to remove the material on the other side. And with that done, the last thing we need to do is flip this over and remove the material from the center to make the yoke. To actually remove the material, I'm using a 1/2 inch corncob roughing end mill. And the reason I chose this over a conventional end mill is because it will produce less tool pressure on the part. And you can see I'm only holding it by the bottom edge so that I can reach down to the depth of the slot that I need to cut. So having less tool pressure means it's less likely to jump out of the vise. I'll also take this in 100 thou step downs. Even though this end mill could take the full depth in a single pass, I don't want to do that because at this point I don't want to pop this out of the vise and have to start all over. So I'll just step down 100 thou at a time until I get about 5 thou shy of the depth I want to go to. I also milled this a little bit narrower than I wanted, so I'm going to come back and bring it a little bit closer with the roughing end mill, and then take that out and put in a smooth flute finishing end mill to bring it to the actual final dimension. So I'm taking 5 thou off the floor, and I'm taking most of the remainder off of the sides. I didn't want to bring it absolutely to the correct dimension in one pass. I want to get it real close and then measure and see how close I am. Just driving the DRO to the correct dimension won't necessarily give me exactly what I want. Though in this case, it turned out it did. It was dead on. So take the measurement, and then I'll come back, and for the very last pass to bring it to dimension, I am doing a climb cut here, and that will leave a little bit better surface finish on the sides. Now, because this is cold finished material and has some stresses in it, I sort of expected it to move a little as I milled it, but it really didn't. This is a really nice fit. Test it with the shoulder screw, and yeah, that works great. Just need to pull this out, do a little bit of deburring, and we should be ready to assemble it. We'll start by mounting the aluminum spacers on the arm, and unfortunately, I had a little mishap with one of them while the camera was not rolling. I started putting in the holes, and it actually moved in the fixture. And since I didn't have a really great way to recover the position, I went ahead and just put 3 more holes and left the 1 through hole in it. I'll just position that hole so that it's not visible once the arm is installed on the grinder. The spacers are each mounted with 3 number 8 flathead screws into the 6 holes in the arm so that they're staggered and the screws don't collide with one another. You won't really be able to see that there are 6 holes in the arm once it's installed. In fact, you won't really even be able to see these screws once it's installed. We'll get those torqued down nice and tight and make sure that the screw heads are below flush so there will be room for the bushing flanges. And then we'll mount the tracking assembly. The yoke goes on with two quarter 20 button head screws, and these just go through the laser cut holes in the arm into the threaded holes that we put in the yoke. That nice and tight, we can mount the tracking plate. It just drops into the slot. It's a really nice fit, and the shoulder screw goes through, and it's secured with a washer and a nylon lock nut. Now it's possible to adjust the fit here a little bit just by tightening or loosening this screw, and that's a little bit too tight. I'll loosen it a little bit so we have a really nice smooth motion with no perceptible slop. And that feels pretty good. These aluminum plates will mount the air spring and the handle, and they just go on here with a couple of quarter 20 button head screws. And these are 1-inch screws, but actually I think 1 1/4 inch screws will work better. These don't quite fully engage the nylon lock nut, but I already noticed this earlier and already updated the parts list that I have uploaded to Patreon. Next step is to press in these oilite bushings, and they're about a 1 thou press fit in the aluminum parts. Could just hammer them in, but I'm going to go ahead and use an arbor press because I have one. Isn't it cute? This is a little tiny one from Harbor Freight. And it turns out it's plenty for this. I really didn't know how hard this was going to be, and yeah, they went in easily. There you can see my extra hole that won't be visible once the arm's installed. I'll squeeze it down nice and hard now that they're both in just to make sure they are fully seated. Then put the arbor press back in the drawer. Now to mount the arm, we've got a 1/2 inch by 2-inch shoulder bolt. Just goes through, and again, there's about 2 to 4 thou of clearance there. This will go on with a washer and another nylon lock nut. And this is another situation where we can tighten this screw down and flex the plates a little bit to control the fit. We're looking for no perceptible slop, but nice free movement. And I think that is going to be that. Next up, we'll mount the air spring. I've got a couple of little 3D printed spacers here that'll keep the spring centered in the space between those plates. They're a little bit hard to fish in, and a pair of hemostats makes this job a lot easier. Still requires about 3 hands, and since I was only born with 2, I'll make do. That's an M4 screw. The original design here, I had specified a number 8, but it is just slightly too large to fit through the holes in the ends of the air spring. Got 2 more 3D printed spacers here on the bottom and another longer M4 screw, and we can tighten down the nuts and the air spring is mounted. The handle goes in with a 1/2 inch long aluminum spacer here and another quarter 20 screw. I included drawings in the files that I uploaded to Patreon for turning this, but McMaster-Carr sells a spacer the right size for a couple of bucks, and it's a time saver, so I just went ahead and ordered it. That feels pretty good. Next up is the tracking wheel. Got a 1/2 inch screw here and a spacer, and that will just go right into the tracking plate. It's all flopping around right now because I don't have the tracking knob installed yet. Get that cinched down nice and tight and put in the tracking knob. This just threads through the arm and pushes on the back of the tracking plate, hinging it up into the correct position so we can control the angle of the tracking wheel with this knob. It's a very simple mechanism, but it works really well. The air spring that I have installed here is a 10-pound spring, and it doesn't really feel like it's enough. So I have a 20-pound one here that I also ordered. I think that, after playing with this a little bit off camera, is a much better choice. Though the way this is structured, you could actually mount 2 or even 3 springs up there to make up whatever tension you want. Well, that's 3 wheels installed. There's only 1 more to go, and we will work on that next time. In the meantime, I'm just going to stand here and admire this thing. I still cannot believe how good these Send Cut Send parts look.
I will definitely be using them in the future.
Are you excited? I'm excited. I've been working on this project for more than a year and I'm having a real Hannibal Smith moment here. Next time we'll install the motor and the electronics and see if we can get this thing grinding. If you enjoyed this video, give it a thumbs up, subscribe so you don't miss the rest of the series, and consider supporting the channel over on Patreon. Patrons can download files for this and all of my other projects and get a little peek behind the scenes. Thank you for watching.